Hey, welcome back, everybody, to your favorite calculus class. Let's get started here with indeterminate forms and L'Hopital's rule. In indeterminate forms, if you remember back to the initial chapter when we were working with limits, is when um, you get a 0 over 0 situation or an infinity over infinity, plus minus on those infinities, and you get an indeterminate form. So, for example, if you're looking right here, oops, see if I can get my, yeah. If you're looking, oh my gosh, what's wrong with my pen? Try this one more time. Sorry about the delay there. But yeah, if we plug in -1 on that, we get an indeterminate form, right? We got a 0 on the bottom, we got a 0 on the top. And so what we did when we were indeterminate form is we would factor that as it shows there, right? We got x minus 1, x plus 1. And then the x plus ones cancel, and then we plugged it in because we're taking the limit as x goes to -1, right? So -1 goes in, so we got 2 times -2, so we get the -4, right? Another way that we would do it if we couldn't factor or if we couldn't multiply by a conjugate, multiplying by a conjugate was another approach that we did, right? And we're in indeterminate form, like right here, where we've got the infinity over infinity situation. What we did was we divided by the greatest, we looked at the denominator and we found the x value with the greatest degree. So that x squared on the bottom, we divided everything by x squared. Everything by x squared, so top and bottom. So it ended up being 3 minus the 1 over x squared, like it shows, over 2 plus 1 over x squared. And then as we took this limit as x goes to infinity, 1 over infinity squared, that's going to 0. That's going to 0. So you're just left with the 3 halves, right? Degree. So, and for that function, of course, that'd be our horizontal asymptote as well. Here's another one with the transcendental functions. Um, Again, you plug in 0, and you got e to the 0. Well, anything to the 0 is 1. So you got 1 minus 1 on the top. You got e to the 0 on the bottom, minus 1. So we got 1 minus 1 on the bottom, right? So we got 0 over 0 as our form. So you notice this will factor, right? And then those cancel. Now we can plug in e to the 0 and get 1. So our limit ends up being 2. All right, so we're just kind of reminded here. Well, not all indeterminate forms, as it says there, can be evaluated by algebraic manipulation. So this one's an example of that. Even if we divide everything by x here, divide this by x, it gets us, it gets us nowhere because we got e to the 2x minus 1 over x. Plug the 0 in, and we've got 1 over 0 minus 1 over 0. So we're like, okay, this is not producing, this is producing just simply going to other indeterminate forms. We can think about this with a table as we're approaching 0, right? If we approach 0 from both sides, as we approach 0 from both sides, looks like we're going to 2, right? So it looks like our limit's going to be 2 on this for this function, for that function as we approach 0. But how can we do this? Well, that's where L'Hopital's rule comes into play for this section here. So L'Hopital's rule states if we have something in indeterminate form, and let me go to it right here, just like that last problem that we had, the limit as x goes to c, as long as we're in the form 0 over 0 or infinity over infinity, and plus minus on those infinity over infinities, then it's the same as taking the limit as x goes to c of their derivatives, okay? So, for example, in this one, we initially, with direct substitution, you plug in the 0, you get e to the 0, so we got 1 minus 1 on the top, got a 0 on the bottom, so again, we got 0 over 0, we're indeterminate. So what can we do with this? Well, according to L'Hopital's rule, if I take the derivative at the top, so ln e, e to the 2x, chain rule 2, derivative of minus 1 is 0, all over derivative of x is 1, and we know that ln of e is just 1, right? So we got 2 2e to the 2x all over 1. Now we throw in 0. So the limit of the derivatives, when you're in indeterminate form according to L'Hopital's rule, the limit can be determined from taking the derivative of the top and the bottom and then do that substitution there. So now we throw in 0. Of course, we know e to the 0 is 1. So this ends up being 2. Limit ends up being 2. Okay, as you can, and as we could see here with the graph of it, right? The limit as x goes to 0, limit ended up being 2. It's approaching 2, or with the table of values. Right? So that's L'Hopital's rule. Let's do it with this one. Now I know we can use an algebraic approach with this, but we're going to use L'Hopital's rule. So if you notice, if we throw in infinity, we've got infinity on the top, we've got infinity on the bottom. So we're indeterminate form. So we're going to say, let's apply L'Hopital's rule, take the derivative. We throw in infinity. We've got infinity on the top, got infinity on the bottom. Okay, you can repeat it. So no problems with the repetition here. So we got 4 over 6x. Now we throw in infinity. So it's kind of like 4 over a million, 6 million, if you will, right? You're throwing in this huge number. We're letting x get larger and larger and larger. Well, what does this go to? That's going to go to 0. 4 over this huge number, so we can now take the limit, right? So you can repeat L'Hopital's rule there. Now here it is, if we divided everything by x cubed, by x cubed, by x cubed, everything by x cubed, right? Then we end up right here. Oh, I'm sorry, where are we at? Duh. Right here. And you notice that goes to 0, that goes to 0, that goes to 0, that goes to 0. So it ends up being 0 plus 0 over 1 plus 0 plus 0. Again, limit 0. But again, L'Hopital's rule might be the way to go, where you take the derivative, it's still infinity over infinity, take the derivative again, now throw it in, and you got 4 over 6 million, if you will. In other words, it's going to 0. All right, let's use L'Hopital's rule here to evaluate. Again, make sure when you directly substitute right now, sine of 0 is 0, minus 0 over 0 cubed. Okay, we got infinity over, or I'm sorry, we got 0 over 0. So L'Hopital's rule does apply. So let's go ahead and take the derivative of sine, which is cosine. Take derivative of x cubed, which is 3x squared. And now let's throw in 0. So cosine 0 is cosine 0 is 1. So this becomes 1 minus 1 over 0. Okay, we got 0 over 0. So I say, all right, I got to do it on this one again. All right, so repeat L'Hopital's rule again. Derivative of cosine, negative sine. Derivative of negative 1, 0. So we got negative sine over 6x. Now we throw in 0. Well, sine of 0 is 0. So the top is 0. 6 times 0 is 0. Okay, 0 over 0 again. So run L'Hopital's rule again. Negative stays there. Derivative of the sine, cosine, derivative of 6x is 6. Throw 0 in now. So this becomes negative cosine of 0 over 6. Cosine of 0 is 1. There it is. Negative 1, 6. Negative 1, 6. Okay. So again, remember you can repeat. Now, these forms have been identified as indeterminate. There are similar forms you should recognize as determinate. Okay, and remember, L'Hopital's can be applied when we've got 0 over 0 or plus minus infinity over plus minus infinity. Okay, so let's look at this one here. If we throw in 0, we got e to the 0 over 0. But remember, e to the 0 is 1. So this is 1 over 0. So we cannot apply L'Hopital's rule. So again, make sure you're watching the conditions on L'Hopital's rule as you're using it in this section. Thanks so much for listening. We will see you guys next time.